So in summary, this first step actually finds dense units in all subspaces, as long as there are dense units, obviously. Yeah, and for that purpose, as I said before, we start with the one-dimensional units, dense units, and then try to merge them based on this candidate generation here in order to form higher dimensional subspaces, or at least higher dimensional units, and then look if they are still dense. If yes, then we continue to expand them. If not, we stop, of course. Yeah? So the whole procedure obviously stops if there are no more dense cells, dense grid cells, dense units in some in some given dimensionality. Yeah? So it starts with 1, then 2, then 3, then 4, then 5, and maybe there are no dense 6-dimensional units anymore, then the whole thing stops, of course. Yeah. So that is dense units, dense subspace units, so to say. Yeah, that is the first step, cluster subspace search somehow. And then the second step is to find clusters, and we said that yeah, we just have to connect or merge connected dense units. So we have to find a maximum set of connected dense units. So given a set of dense units in the same k-dimensional subspace, we compute from this set of dense units, we compute the final subspace clusters in this particular k-dimensional subspace. Yeah? So we, of course, cannot mix dense units from different k-dimensional subspaces or different subspaces of different dimensionality, because we would mix apples and oranges here. But we just look at one specific subspace, yeah, and look and take all the dense units in this particular subspace to find clusters of maximal connected dense units. So the output of these dense units, or we transfer this set of dense units into clusters of connected dense units. K is need not to be the same of the dimensionality, of course, need not to be the same in all subspaces, but it's just an arbitrary thing here. So the number of clusters per subspace is determined automatically, of course. So how this is done? Well, actually the problem is equivalent to find connected components in a graph where the nodes are the dense units of some specific subspace, yeah? And the edges between two nodes exist if there is if these two dense units are connected. Yeah? So connected means here in that case have a common face. So there is no diagonal matching, just matching according to a common k-1 dimensional face. And finding connected components in a graph can be done in different ways. So in this case, there's a depth first search algorithm. So we start with the unit U in D, assign it to a new cluster ID, and find all the units that are connected to this unit U. Depth first, yeah. So we just put all points, all units that have an edge to the initial node or initial unit U into a priority queue or a queue, yeah, and then put all connected components, all connected units in a queue, and then just work out the queue. Yeah? And if we find new connected components, new connected units, these are also added to the queue, and we do that until the queue is empty. Then we found one cluster. Yeah? And if there are nodes that are not yet visited in the original set here, then we repeat this best first search, obviously. Yeah? So that is very easy even to implement. So short discussion on that here. So input parameters are the density based or the density thresholds. Xi is the number of intervals. So it implicitly defines the volume, and tau is the minimum number of points that need to be there to say that a unit is dense. And the output is all clusters in all subspaces. So clusters may overlap. There may be points that are in one specific cluster in one specific subspace, and in a completely different cluster in another subspace. Yeah? Yeah, the cluster model is quite simple, but rather efficient, at least efficient, easy to implement and stuff like that. However, and that is the basic criticism of all the density-based subspace clustering algorithms, we will see the same with the next one here, is that Clique and also subclue as next use a fixed density threshold for all subspaces, and that is important in order to ensure the downward closure property, because otherwise if we use an adapted threshold, the downward closure property doesn't hold anymore. So we need a fixed density threshold, so xi and tau are fixed for all subspaces. And if you think about it a little bit closer, well, take this one here. To represent a cluster, a unit in 10D must contain as many points, or even more, as in 2D. And of course, in 2D, we know from the curse of dimensionality that in 2D, the unit has a much lower volume than in 10D. So we compare again apples and oranges a little bit here now, because we think, or we require a 10-dimensional or high-dimensional subspace to contain as many points as low-dimensional subspace clusters. And that is probably something which is a little bit unrealistic, or at least this fixed density threshold is somehow a trade-off between many small dimensional clusters, but also a couple of higher dimensional clusters, or no higher dimensional subspace clusters, the other way around. Because for a cluster in subspace S, all clusters in all projections of S are also reported as clusters, because from those candidates we generated the higher, from those lower dimensional dense units we generated the higher dimensional ones. So that is obviously an extremely high redundancy, because for any cluster we report all the subclusters in all projections of the subspace, and that is extremely redundant, obviously. And the question, of course, if we have a very high redundancy, a very high number of resulting clusters, which one are the more interesting ones? So which of the redundant information that we get is more interesting? Is it D in some subspace S, or is it a projection of D prime in T, which is a projection of S? Why is that important, or why is that interesting? Well, D prime may contain, of course, more units, more points, and the question is, when is the more the merrier? So there are a lot of follow-up papers actually along that way, trying to come up with some kind of measures, which of these clusters that are reported are more interesting than the others. And that is, of course, extremely subjective, and not so easy to decide sometimes. And once again, we, like in the frequent item set mining problem, we get all the frequent item sets, which is of length k, all the redundant k-1 projections of k, and k-2 projections of k, and so on and so on and so on. And so there's an extremely high number of resulting clusters, probably, depending, of course, on the threshold. We somehow need to take care that we are not lost in this sea of clusters that we get. And most of them are extremely redundant, because they are just low dimensional projections of the higher dimensional ones. So these are the two basic problems of these methods here: the fixed threshold, and this highly redundant, high number of redundant information that we get out of as a result. And once again, both or most of or all density-based subspace clustering methods suffer from these two problems actually. What is the worst runtime complexity? Well, still, in the worst case, we have an exponential runtime, because in the worst case, the whole procedure stops only until we got a full dimensional cluster. Yeah, so until we get to D, the dimensionality of the original dimensionality of the data set. Yeah, so that is the worst runtime thing, runtime complexity. If the density threshold is very, very loose, we probably also get some full dimensional clusters, and in that case, the whole thing has to explore all the exponential the exponential number of subspaces actually. Yeah? So that is somehow the downside, and we have to be very, very careful in the end with this density threshold here. Yeah? Because the more loose it is, the higher the runtime, and the higher the dimensionality gets that we get clusters from. And if we use a very strict density threshold, then probably we only get the 1 or 2 dimensional clusters in a very short time in that case. Yeah? So there is a clear trade-off between those two things.